Okay, so next Monday, we will go over questions for the midterm review session. And then you will take a quiz number 1 from chapter 1 to chapter 7. No calculation, just concept and terminology. And this one is online because next Monday class is online. But this quiz is real time. So when I say start, then start, okay? So quiz number 1 is now real time, online. The number of questions is about 30 questions from chapter 1 to chapter 7. So before that time, I recommend you prepare lecture notes because it's on open book, open notes. Okay, any question about the quiz number 1 next Monday?
You said the quiz is open now?
Open book, open notes.
Okay.
So prepare lecture notes or a PowerPoint. Or before taking that quiz, you may review lecture notes or PowerPoint. Okay. And midterm next Wednesday. This one is optional. You can take midterm in class or online. This one also real time. So if you take this one online, then I will send you, email you questions. And if you want to take midterm in class, then email me. You want to take the midterm in class. I will prepare paper midterm. So I need to count how many will come. Okay, so if you want to take midterm in class, email me. Then say I want to take midterm in class. I will prepare a paper midterm. And also, if you take this midterm online, I need your face. So this time, you know, you turned up camera, but when you take a midterm, I ask you turn on your camera. And then, you know, because this one is an online test to prevent cheating, I will make several sets of different questions. And then I will send you, email you questions just right before starting time, okay? So, maybe it is not possible to cheat. Okay, so prepare, review your assignment, practice problem, so prepare well. to get a good score and a good grade. Midterm questions, 4 questions from assignment 1, 2, 3, 4. Similar, not the same, but similar. So if you can do assignment 1, 2, 3, 4, then maybe no problem to take midterm. Any question about midterm? Okay, good. And now let's go to chapter 7. Okay, just a moment. Okay, chapter 7 is about service process. Last week, we talked about process and production process. Service process, when we say service business requires interaction with the customer to produce the service. Earlier, when we talked about the operations, then production system and service system. At the time, output is tangible, then production, intangible, service. And then in addition, that talked about the interaction, customer interaction, then it is service. So service business requires interaction with the customer. Types of service, facility-based service, field-based service. Facility-based service, customer must go to the service facility. So usually when we buy something or when we have to have service, we go service facility. So that is facilities based service. Field-based service, production and consumption of the service take place in the customer's environment. Sometimes, such as vacuum service, I need a vacuum, steam vacuum for my house. Then call, and then they come to my house, and then they service. So that case, provider goes to customers. So that is field-based service. And internal service, even a production system, if there is a customer and provider interaction, contact, then it's service. It's like in production system, multiple activities like this. Then from suppliers or providers, then. So this company process or production system is customer, and then they are suppliers or providers. So at this point, there is customer and supplier contact, interaction, and then also receive part, and then do something, and then send it to next stage. Then if there is contact or interaction, then provider or supplier, and then customer, and so on like this. And then in the like office, they work together. Then the paper move, then contact and interaction. That case, we call that as internal service. So the management of services required to support the activities of the larger organizations, such as the manufacturing system or any company. If there is kind of activities, contact, and interaction, then it is internal service. The services including data processing, accounting, and so on. And operational classification of service, customer contact, physical presence of a customer in the system. Not only physical presence, like this online contact, that also kind of customer contact, you and I through the internet, virtually, there is no contact with you and I. And then customer is involved in the process. So here, some students here, and then over the internet, you are involved in this process, teaching process. So there is customer contact, you and I. And then high degree of customer contact, low degree of customer contact. Like at regular time, you come to classroom and then face-to-face. That is a high degree of contact. And then like you and I through online, that is low degree of contact. So if the degree of contact is high, then more difficult to control, more difficult to rationalize, and then also more difficult to standardize. Low degree of contact, less difficult to control, less difficult to rationalize, and also less difficult to standardize. So based on the degree of customer contact, if higher customer contact and low customer contact, based on degree of contact, we can divide the buffered core, permeable system, and reactive system. Buffered core, none or a little contact. Many cases they call you, try to contact you to sell something. So over the phone or over the internet, like using email and so on, that is none or little contact. So that case, that process is the buffered core. And then permeable system, some contact and reactive contact, much contact, face-to-face or physically contact for the service. So based on this degree of customer contact, we can divide like this. And then examples, low or less contact here, mail contact, internet contact, phone contact, and face-to-face, and so on like this. And then sales opportunity, the greater the amount of contact, the greater the sales opportunity. So they try to contact you using a phone call, using internet, and so on. because if they contact more, then sales opportunity increase. And production efficiency, because more contact, then difficult to rationalize, difficult to control, difficult to standardize. Higher contact, then production efficiency low. Because of that, hard to or difficult to make it rationalize, standardize, and control. So more contact, then production efficiency drop or decrease. Designing service organizations, because we cannot inventory services. So when they need service, just give the service. So capacity of service is very important. To find, we need optimal, to find, finding optimal level of capacity for the service system. So it's like, I think I gave this example earlier. You know, if capacity is like 1,000, but customer size is 2,000, then long waiting line, then maybe lose opportunity because of low capacity. Or if the capacity is 1,000, but customer size is 1,000, then 1,000 is unnecessary, like waste or cost. So we should find optimal level of capacity for the service system. So we need this technique, like waiting line models, queuing system. We will cover this one a moment later. Service strategy. When we design service system, then we should consider these things. Treatment of the customer, of course, with kindness, and then courteous and so on. And then speed, faster, price, lower or cheaper. Quality of tangible goods associated with that service, high quality, so better, cheaper, faster, and also kind of kindness and so on. Three contrasting service design, the production line approach. McDonald's is a service system because there is customer contact, interaction, but McDonald's produce hamburger and French fry and food. So McDonald's use kind of manufacturing process. Focus on things like they use production line system. And self-service approach, like an automatic teller machine, automatic something car washing machine and so on. Because if they use an automatic machine, then they can reduce the labor cost. So focus on low cost in this approach. Then the personal attention approach, such as a Ritz-Carlton hotel, any hotel nowadays. Once you stay hotel, then if you leave your information, then later they try to contact you like a birthday promotion, send you information, and so on. So using such as guest history information, try to contact and then track the customer's personal preference to increase like opportunity. Okay, waiting line situation, waiting line. You know, more service against the inherent cost of waiting. So earlier, the example of the capacity. If current capacity is 1,000, then if customer size is 500, then 2,000 like this. If customer size is demand is more than this capacity, then waiting line, longer waiting line. But much less than this customer size is much less than capacity, then there is something cost, unnecessary cost. So this case, you know, to match customer size, it need an increase more capacity. So if increase capacity, that is cost. But this waiting line is decreased. So it's like a waiting cost. It's like a seesaw. So waiting cost, and then service cost, facility to improve the capacity. So increase this capacity increase, then waiting cost and then decrease. If this one decrease, then increase like this. So waiting line situation is a trade-off decision. The waiting line system or queuing system, three parts, consists of three parts. Customer arrival, it says source of population, and then system itself, serving system, then exit system. Source of arrival, customer arrival part, source of arrival, finite or infinite. Usually, customer size is infinite, but sometimes it is limited size. When I say, I can ask you like this, this Scranton population is, let's say, 70,000. Then it is finite or infinite. And when I ask this question, some student says it is infinite, it is finite like that. So it is depending on capacity. If a system can handle one customer a day, then it takes like 70,000 days. So that case, customer size is infinite. If a system can handle 100,000 in a minute, that case, the population is finite. And distribution of arrival, the number of arrival rate, the number of units per period, like 10 customers per hour, 1,000 customers per day, like that. So in a certain unit of time or period, how many customers come? That is an arrival rate. And then arrival rate sometimes follow constant arrival distribution. The same number of customers come in every unit of time, but usually arrival rate follow variable arrival distribution, such as exponential distribution and Poisson distribution. So random arrival. Customer arrival in queue distribution constant exponential Poisson distribution, and then pattern controllable, uncontrollable. If we can control customer size using a different price, when we go movie theater, early, then it's cheap. Late and then regular, or sometimes is kind of premium high price. So using different price control customer demand. If we can control, then the demand is customer size is controllable. If we cannot, then uncontrollable. And size arrival, sometimes one by one, sometimes batch by batch. Degree of patience. When you go market, then if you look at the waiting line, long, and then some people just wait and then buy. But some people look at that line and then just leave. Or some people just wait and then next time and then leave like that. So impatient, arrive, view, and then just leave right away, and then arrive, wait some time, and then later leave like this. And then system itself, length of queue, the waiting line can be infinite, can be limited line capacity. Like a Black Friday, then waiting line is long, and then maybe there is unlimited, infinite potential length. But sometimes, some case, the waiting line, the queue is limited. In this case, like a traffic system, a street, traffic light here and traffic light here. So when it's red, cars stop here. Then when the light change, here, green, then cars go. But this light is still red, then cars stop here. And then if this space is like only 4 cars stop there, then it's usual, even it is green, cars stop here and then clear this intersection. So this case, this traffic light system waiting line is limited. So this case, limited line capacity. And then number of lines, single line and then multiple lines. You know, McDonald's and then Burger King use different waiting line system. McDonald's, if there are multiple order station or a pay station like this, then if they open or then form waiting line for each station. But Burger King, even they open multiple, form all line here, and then when it's open, and then distribute like this. So Burger King use single line, and McDonald's use multiple lines like. And Q discipline, first come, first serve, FCFS. So usually we use this FCFS, and then shortest processing time. If there are multiple processes, then take shortest first and second and third and so on. That is shortest processing time rule. And reservation first. If they have reservation, then give a service for a reservation holder. Oops. And then I have a question like this. You know, when we reserve and then make a call, then we use different words. If we call a doctor's office, or you want to see me, then use an appointment. Can I make an appointment like this? But then when we reserve airline ticket, then we can say, can I reserve? So why we use different words, appointment and reservation? If we reserve person, like a doctor and your professor, then you're using appointment, so appointment system. If you reserve place, like a seat, like airline seat, and then reserve, you know, when you go out a picnic, then a picnic table reserve. So that case using a reservation. So reserve person appointment, and then reserve place, then reservation. And emergency first, like an emergency room, multiple patients come, and then decide which one is which patient is more urgent, like more blood or less blood, like that. So emergency first, then limited needs such as like a ticket. So ticket holders first, and then next. So limited need maybe similar to reservation system. And service time distribution. Service time may be constant, maybe random. The same service time. If give service using automatic machine, when you go car wash, then the car washing machine, then if you choose the same package, next time, this time, same time, service time. And then random service time, exponential distribution. Sometimes it takes 5 minutes, it takes 4 minutes, it 30 minute, 30 second, different time, random service time. And line structure, single line, waiting line is single, and then single phase, multiple phase. One like when you go fast food restaurant, this time usually a single phase because dine in is not allowed. So drive through, order, then receive, and then leave. So ordering phase done. But if you go restaurant and then if it is dine in, then order system, order phase, and then eating and so on like that. And then multiple channel and then the same single phase, multiple phase. And mix it, multi to single. Like a construction site, you know, I live in south of Scranton. It takes about 45 minutes. Take an 81, I-81. So after class, I have this class and then 6 o'clock class. So when I finish the night class, then when I take the 81, this time I think they start the construction there around 7 p.m. So it's like multiple multiple lines, and then here construction site. So this one was one line like this. It is to a single like this. And then alternative path, like the process need customization because there are many different types, but each type volume is small size. That case, they pass different like this alternative. Okay, exit line structure, the last part of the waiting line system, queuing system. Exit, usually single channel, single, and then single phase, just out and then done. And then sometimes the customer come back for the reservice, but low probability. Okay, waiting line models. Waiting line models. There are many different models, but our textbook and they are 4 models are basic models. Based on factors, layout, how many waiting lines, single or multiple, and then source of population, if it is infinite or finite, and then service pattern, service time, exponential, random service time, different service time or constant. And then other factors, service phases, single, arrival pattern, poison, queue discipline using F SCFS, first come first serve, and length of the queue, unlimited. Other factors are the same, and then based on how many waiting lines, and then source population and service pattern, we use different models to solve the problem. By the way, this source of population, earlier I exampled the strengthen population. But actually, if I'm a technician to maintain copy machine in this Marriott University, then if there are only 10 copy machines, that case, source of population can be finite. So that case, we use model 4. And then other factors, basic factors, then use model 1. Example number 1, customers in line, a drive-through window service. You know, usually drive-through window service, only one channel, only one waiting line. But recently, McDonald's used two drive-through lanes. So except that case, usually drive-through window service is only one channel, only one waiting line. And then arrival rate, 15 cars per hour. So arrival rate is 15. And service time, 3 minutes on average. This one, this example doesn't mention about the arrival service pattern, but assume this is random service time. That case, layout is single channel. We assume drive-through window service is a single channel, and source population infinite. Service pattern, we assume service time is random, so exponential distribution. That case, from the chart, single channel and source of population infinite, service pattern is exponential random, and then other factors the same. Then we use model 1. First, we need arrival rate and service rate. Arrival rate is given 15 cars per hour. Time unit is hour. And then arrival rate, we can read this notation as lambda. Lambda equals arrival rate, then equals 15 because it is given. And service rate, mu, that is, time is given, not rate. Time is given, and then time unit is hour, because arrival rate 15 per hour. So 3 minutes, and then 60 minutes, that is an hour. It's like that. How many customers can be served if the service time on average is 3 minutes? So during 60 minutes, 1 hour, 20 customers can be served. So 3 minutes. It's like that. How many 3 minutes in an hour? So 60 divided by 3 minutes equals 20 customers can be served. And then ratio of total arrival rate to service rate. So arrival rate to service rate, that is average utilization of this system. This utilization, average utilization of the system, denoted by this notation, rho, not P, it's rho, equals arrival rate divided by service rate. So 15 divided by 20, 0.75. So 75% utilization. This system work 75% of capacity. Okay, using this model 1, we can get information about average number waiting in line. How many customers in waiting line? LQ, length of queue, equals arrival rate square divided by service rate times service rate minus arrival rate equals arrival rate is 15 square divided by service rate 20 times service rate 20 minus arrival rate 15 equals 225 divided by 100. So on average 2.25 cars or customers in waiting line. So on average, there are 2.25 customers wait for the service. And then average number of in the system, how many customers in the system, including customers in waiting line and then being served. LS, length of system, equals lambda over mu minus lambda arrival rate divided by service rate minus arrival rate equals 15 divided by 20 minus 15 equals 15 over 5. So on average, 3 customers or cars in the system. Someone is served and then someone waiting line. And average time waiting line to get service, how long they wait in waiting line. WQ, wait in queue, equals length of queue divided by lambda, arrival rate. So 2.25, this one we got earlier, 2.25 cars on average divided by 15 equals 0.15 hour. If we want to convert in minute, then times 60 equals 9 minutes. So on average in this system, to get service, 9-minute wait in waiting line. And next one, average total time in system. This one, including waiting time and service time. So LS, total customer in the system divided by lambda, arrival rate. So 3, LS was 3 and divided by 15 equals 0.2. Hour times 60 equals 12 minutes. So waiting time, 9 minutes. And then total time now 12 minutes. You know, service time on average was 3 minutes. So waiting time 9 minutes plus service time 3 minutes, 12 minutes total time in the system. Okay, the show, and you have practice problem, this one. Looks like this. So for this one, model 1, practice problem. Now it's two. Okay, I will go over this practice problem next class on Wednesday, and then finish other part on Wednesday. Okay, any question?
What day did you say the quiz was? Was it this Wednesday or was it next week?
Quiz next Monday.
Next Monday? Okay.
Yeah, I will show you the schedule again. So quiz next Monday. Midterm next Wednesday.
Okay, thank you.
Thank you. Okay, any other question? Okay, good. See you Wednesday. Wednesday class is online only.
Thank you.
Okay. Thank you.
Have a nice day.
You too.